In this installment of the Crash Course Regents Chemistry series, I will be reviewing all of the reactions, chemical reactions, and their names as it pertains to the New York State Regents Chemistry Curriculum. And this is a special request, and I am getting to it. So let's get started. The best way to start this is understanding we have some names that pop up. For instance, we have something called synthesis. Okay, and then we also have analysis. Now, synthesis, as the name implies, meaning we're making something, normally from its elements. So if I take, let's say, nitrogen, and I take oxygen, and I want to make NO2. All right, normally, let's balance this. So we're going to need a 2 here and a 2 here. Okay, and this is a synthesis reaction because I'm making something from its elements. Now you could also call this a formation reaction. Okay, that's certainly plausible. Okay, but synthesis is a better name for it. You could also call it a redox reaction. Now, redox reactions means that oxidation states are changing, and as I've taught many of you, you find me a zero, or find me an element or something in its elemental state, it's a zero, and when it's bonded to something, it's something other than zero. Okay, in this case, it's +4. So if you find a zero or an element anywhere in the reaction, you know you have a redox reaction. And we can also call this a composition reaction. All right. Now, analysis is just the opposite. Okay, if you take your NO2 and you break it down to analyze how it was made, and you get back your elemental states. Notice the diatomic elements are listed here. Anytime you write a diatomic element, you have to write it bonded to itself. Okay, and the same balancing applies. This is analysis, meaning we're taking something and we're breaking it down to see what it is made from, to analyze it. Now, you can also call this decomposition. Okay, decomposing. So the opposite of these reactions is decomposition. Now, a nice place to look where these reactions will occur is table I. So if we look at table I, in the middle of table I, we have a bunch of synthesis reactions or redox reactions, okay, or formation or composition reactions, okay? And my friends in chemistry, elements are making compounds, and the reverse of these reactions are decomposition or analysis. One thing I will say, if something is being synthesized, if it's exothermic, delta H is negative, meaning energy is released. In the forward, in the reverse, it becomes positive. So the decomposition, all right, of aluminum oxide, or the analysis of aluminum oxide in the reverse, would be endothermic, positive 3351. Okay, so something to think about there. Now we also have combustion. Combustion is usually some organic fuel, I don't know, like propane, C3H8, plus oxygen, okay, making CO2 and water. Normally CO2 and water and our respiratory gases that we excrete, okay, from our lungs is because of the slow oxidation of glucose in our bodies. Of course, I didn't balance here, so I have 3 carbons, 3 times 2 is 6. Okay, so this gives me 6 oxygens on this side. Now I have 2 H's, 8 H's, so put a 4 in front. That gives me 8 H's, but 4 oxygens over here, so a total of 10 oxygens. And to balance that 10 oxygens, I put a 5 here. So these are combustion reactions, some kind of organic-based fuel plus oxygen, CO2, and water, and all of these are exothermic. Okay, it's burning. And table I shows you another place where these reactions pop up. Top third of table I is showing me some combustion reactions. Very nice. Okay, O2 plus the carbon-based fuel gives me CO2 and water, and very exothermic. While we're at table I, we also have something called ionization reactions to the bottom third here. These ionization reactions are nothing more than salts, okay, being dissolved. So you have these salts, these ionic compounds in water, breaking apart into their ions. They're all electrolytes. Some of them make the water colder, some make the water warmer. If it's exothermic, that means when it dissolves, that chemical is releasing heat into the water. Okay, ionization reactions. These are involving electrolytes. Next reaction I'm going to talk about is double replacement reactions. These are aqueous salts, so these should be aqueous. They're solutions. They're really free ions because they're soluble. If I have a beaker of lead nitrate, what I really have is lead plus 2 ions in solution and nitrate ions. Nitrate ions are always soluble. If I had a Ki solution, I'd have K plus and I negative in solution. Now when you pour them together, the positive ions are going to find the negatives, and we're going to double replace do-si-do. Make sure we write correct chemical formulas. Lead is plus 2, iodine is negative 1, so you'll need 2 of those. And of course, you're going to make KNO3, so I'm just switching the partners, okay? But in this case, the lead, when it finds the iodine, is going to stick together because they attract each other stronger than water can attract these ions, and they become something called a precipitate. Okay, so they double replace and a precipitate is made. And by the way, if precipitate is being made, we say the reaction is going to completion because it'll keep going until you run out of one of the two compounds here. It doesn't go in the reverse because this is locked in a three-dimensional crystal lattice. How do I know this is a precipitate? How do I predict if a precipitate is formed? And make sure I balance this. Two nitrates, I keep the polyatomic ions together. 2 Ks, 1 K, 2 iodines, 2 K, everything's good. Notice when I balance this, I treated the nitrate ion as a single entity, and it makes life a little easier. But in any case, how do I know this is a precipitate? How do I know it's a solid? This does not mean soluble, it means it made a solid. All right, and this is aqueous. I go to table F, or table foo-foo, as I like to call it. In table F, I look at the solubility guidelines. It tells me how well water, that's why the aqueous part, can actually break these solids down into their ions. Now, some ionic compounds or salts it cannot because the attractions are strong. That's why some of the ones that have large positives and negatives are insoluble. So, chloride, we're talking about lead chloride here, lead iodide, sorry. Is it soluble? Well, sure it is. Sure it's not, sorry. Iodine is normally soluble, and it has 3 exceptions. Well, what does that mean? It means, well, it's soluble except when hooked up or bonded with these 3 elements. These 3 entities or ions will cause these other ions to form insoluble precipitates that remain as solids. Okay, so lead iodine, based on our solubility guidelines, makes a precipitate. Silver iodine, mercury iodine, all make insoluble compounds. Okay, so that's how I figure out when I double replace whether or not I made a precipitate or if it went to completion. See if you make a insoluble compound. That's your precipitate. Okay, now we have single replacement reactions where instead of double replacement with both ions of the 2 chemicals switching places, that's a double replacement. We have a single replacement, replacing one element with another. Now we did this in the demonstration of the copper coil in my little beaker, and we watched the silver appear on the coil, solid silver. So the copper kicks out the silver, solid silver, and we make copper nitrate. And copper is probably plus 2, so we need a 2 here, 2 here, okay? And that's our bounce reaction. Now, let's write this nicer. Copper nitrate aqueous. And say, well, how do I know it's aqueous? Table F tells me all nitrates are soluble. This is also soluble. In any case, this is an example of a redox reaction as well. Do you see a 0? Yes, you do, at least one. If you find a standalone element, you have yourself a redox reaction. So one of the classic types of redox reactions are single replacements. And of course, with these types of reactions, is it spontaneous? So if you look at copper and silver, copper has to oxidize. Why? It's the standalone element, can only oxidize. And if you write yourself a quick half reaction, copper 0 goes to copper plus 2. I know it's copper plus 2 because each nitrate's -1 and there should be 2 there, sorry. And I'm going to put 2 electrons on this side because a -2 and a plus 2 is 0. So copper is undergoing oxidation. Charges are changing. And copper is above the silver plus ion here. So on table J, if copper for the metals is above silver, and it is, copper is going to oxidize, while the silver is going to reduce, or the silver ion is going to reduce, and that's what we're saying here. So this is spontaneous. Another type of a redox reaction that's also single replacement that has some importance is making hydrogen. Okay, zinc is going to oxidize for the obvious reasons. There's a half reaction for zinc plus 2 electrons. The H plus is H plus. This is 0. So we write 2 H pluses, gaining 2 electrons. That's reduction. The electrons on the reactant side becoming H2, 0. Okay, and H plus is getting reduced. It's gaining electrons. Its charge is going down. Remember, gaining electrons. Electrons would be in the reactant side. R for reactant. And then Leo the lion, zinc, losing electrons is oxidation. Okay, so is zinc above the one who's reducing H2? Not really, it's H plus, but they write H2 in reference table J, and it is higher. So this does do this. It's spontaneous, but more important, any metal that is above the H2 in reference table J will make H2 gas. And the ones that are below it, which are gold, silver, okay, and copper, are below H2, which means these metals with an acid will not make H2 because they're going to supposedly oxidize, and they have to be above them. Case in point, let's go to reference table, and that's what I'm talking about. Here's H2. Every metal above H2 is going to oxidize, and this will be part of reduction. Okay, so that every metal above the H2 with an acid, the proton, will make H2, but these metals with an acid do not do that because they're below, and the one who oxidizes has to be above who reduces in this table. Okay, so now I'm pretty much out of reactions in inorganic chemistry, so now I'm left with organic reactions. Okay, the first one is substitution. In substitution, we have a saturated hydrocarbon that does not have any room. Okay, and I guess they're cutting the lawn outside today, sorry. And if I'm going to add Cl2 to this, you can clearly see there's no room to add because of the saturation of single bond. So an hydrogen has to be substituted for chlorine, and what happens in this process is that we make 2 products, okay, and a chlorine comes on, and an H comes off, oops, HCl, all right, is made. So 2 products are made because of the substitution, and the substitution is made because there isn't any room. And you need to know that saturated hydrocarbons undergo substitution, okay? Now, in addition reactions, very similar. These guys are unsaturated. They have less H's because they have a double bond between the carbon, so they don't hold on to the maximum. So if I was going to add chlorine to these, this molecule will attack the double bond, and what you're left with, party people, is a carbon single bonded and opened up so that two chlorines can add, but here's the key. The catch is the 2 chlorines add to 2 different carbons, because once you open this up, each carbon has an initial place for it to go. And notice there's only one product, okay, whereas whereas in a substitution there was two products. Very important, and this of course is an unsaturated hydrocarbon. Now, next one is esterification. This is the aromatic compounds that smell nice. Well, guess what happens in these compounds? It's called dehydration reaction. Okay, we take an organic acid, got the H there, meth-eth-prop, this is propanoic acid, and this alcohol, methanol, and they collide, proper orientation, water comes out, and these guys are pushed together to make that ester linkage. We have a CH3, which is right here, CH2, C double bonded to an O, single bond here to CH3. And your ester functional group is right here. Okay, and in table R, they go R to C double bond to an O to the O to R prime. That R represents the rest of an organic molecule. So you need to know an ester is made from an organic acid and an alcohol. Of course, it's plus a water because the water comes off. Okay, and the name of an ester, which is built upon how it was made, you take the alcohol who made it, okay, which is the meth, and you make it fancy by saying YL, methyl. Then you take the acid part, the 1, 2, 3, prop for 3 carbons, ane for single bonds, and OATE, methyl propanoate. How do I know the alcohol? If I was just given this, as I said in my organic crash course, you would cleave the O's. The carbon double bonded part must come from the acid part, so that's how I do it. Okay, esterification. Some of these organic reactions are just denification alone, and fermentation is just like that. Identify a sugar. That sugar can come from grapes, barley, oats, grains, fruits, and with yeast, okay, and the enzyme in yeast is zymase, anaerobic glycolysis takes place, and microorganisms can breathe, they can respire, they can get energy from the sugar, but they give off a byproduct which is called ethanol. Eth for 2 carbons, OL for an alcohol. The OL ending in table R is something you could look up if you're not sure how to name an alcohol. And of course it gives off CO2. Beer has CO2 because of that. Okay, some liqueurs or in some alcohols that we make, products with alcohols don't have the CO2 because we let it leave. Some places we want them. So this is just an example of how we make alcohol, fermenting some sugar with zymase or some yeast to make this byproduct of anaerobic glycolysis, and all you got to do is recognize that. Okay, in polymerization we take something called a monomer, okay, and we basically attach the monomers to make long chains. So these monomers, okay, would connect to another monomer to make a polymer, except these monomers that I'm drawing have double bonds, so they don't have any room until we open up this double bond. So we would start the process by opening up a double bond. When you do so, okay, what you get by these guys adding together, and many of them, is a long chain hydrocarbon. And that's polymerization. Notice I'm opening up the double bond. So this is called addition polymerization. Now, if we've got polymerization where we're taking out water, it's called condensation. For instance, I have a compound here that has a Cu group ending, organic acid, and then I got a CH2, and then I've got a CH2 and an OH at the end. I look at this compound, okay, as my monomer, and it repeats some number of times. And sometimes you'll see brackets and an N that show that this repeats over and over again. It's a polymer. Or however, if I draw another monomer the same way, okay, let's put it in blue, and I have the OH ending, CH2, CH2, C double bond O to the OH. I take out the water, and guess what I make? I make an ester linkage. And this would be a polyester. Notice the water comes out, So this would be condensation polymerization. Okay, condensation polymerization. All right. In saponification, what we have is these ester linkages of what we talked about in terms of the fatty acids in organic chemistry linking with the glycerol, which is really an alcohol, a trihydroxyl alcohol, and a strong base. You're going to see a strong base, and you're going to see somehow it's some kind of formula, which is pretty massive, and that repeats 3 times, okay? And you're going to cleave these, and you're going to make the soap molecule. It's got a negative N. It's got a Cu group and a negative N, okay, and a very, very polar, non-polar end. So polar that reacts with the water, the negative and positives that interact with the water, hydrophilic end, and the hydrophering phobic end, which is the soap molecule, and the glycerol. So you're going to reform the glycerol, and you're going to have the soap molecule, the 3 fatty acids that are now the conjugate bases with the Na plus at the end. So you see some funkiness, and you're making the glycerol. It's basically, can you identify it? That's saponification. So nuclear fission is splitting the atom. We have a big nucleus splitting into smaller fragments. The fragments are barium and krypton, and 3 neutrons. Now, in this splitting of the atom, we know that the nuclear equation and all, we have conservation of mass, so to speak. 141 plus 92 plus 3, right? There's 3 of these. It's 236, and that's 236 above here, right? Because 235 plus 1 is 236. 92 plus 0 is 92 on this side. These have to equal 92. But fission, again, splitting into smaller fragments, 3 more neutrons can find more fissionable big atoms. So large nuclei splitting into smaller fragments, and of course produce more neutrons. So it's a neutron plus a large, usually uranium, into fragments. That's fission. Fusion, as the word describes, is the light nuclei combining to form heavier nuclei, even though they're making helium. So very light nuclei are being pushed together, which requires a lot of energy. Right now, too much energy that we know of to create a reaction and to identify fusion, and they're written many ways. You're looking for some form of hydrogen or light nuclei making helium, and atoms are coming together, not being split like nuclear fission. So all it is identification. Light nuclei making heavier. Fission is big nuclei going into lighter. And of course, fusion and fission follow E equals mc squared. We're missing some mass along the way. Even though I said conservation of mass in the one above, in truth there's some missing mass. It's called mass defect, and that mass times the speed of light squared is the energy given off. Very, very simple. And because fusion gives off more energy than fission, there's even more missing mass. If you want more details on these reactions, please go to my Crash Course Nuclear Chemistry series. But this just reviews the reactions and their names. Hope you enjoyed it.